All right, so as I mentioned here, most of the asteroids have pretty eccentric orbits, but they spend their time between Mars and Jupiter in this region we call the asteroid belt. Called the asteroid belt because most of the asteroids are there. If we add up the masses of the asteroids, it's a small fraction of the mass of the Moon. All right, so here we have a couple of photos taken by space missions of asteroids. The most interesting photo is really the one on the left, and the thing that's intriguing about that is that we're looking at an asteroid there that if you can see that little point of light to the right, it has a moon of its own. A tiny little moon of its own called Dactyl, which is only like maybe, I don't know, maybe a kilometer across or something like that. The remarkable thing about that is that we have a moon around an object that has such a weak gravitational field. We'll talk about the surface acceleration at the surface of an asteroid in a little while, and you'll see that the surface acceleration at the surface of an asteroid is tiny, minuscule compared to the surface acceleration of the Earth. So if you drop your laser pointer near an asteroid, rather than dropping it, accelerate at 9.8 meters per second squared, it is barely going to accelerate at all. It's just going to drift down ever so slowly near that asteroid. Because even though we think of asteroids as being pretty large rocky objects, the thing is the gravitational force is so weak, really, that even a rocky object like what we're looking at here is not nearly massive enough to generate a really strong gravitational field. Okay, so, looking back to the photo, how can it have a moon? That moon is barely bound to the asteroid, so it's pretty hard to see how something like that can happen. So let's get a little deeper into asteroids now. First asteroids were discovered in the 1800s. This is a period of time that's, of course, post the development of the telescope, post Galileo. So this is these are objects that were discovered telescopically. You basically cannot see any asteroids, more or less, with the unaided eye, even the large ones. First one discovered was Ceres, semi-major axis of 2.8 astronomical units. Now, already keep in mind that we're talking about Mars having a semi-major axis of 1.5 astronomical units, okay? And then Jupiter's out at 4.5. So this particular body here has a semi-major axis of 2.8 astronomical units. That's between Mars and Jupiter. So this is already our first example of a body that's orbiting in the asteroid belt between Mars and Jupiter. Other large asteroids were discovered within a few years, Pallas, Juno, Vesta. These comprise the big core of asteroids, as we'll see. We know of hundreds of thousands of them, but the ones that I just listed here are the really large ones, so multi-thousand kilometer type ones. The floating continent-sized asteroids, and there's only a few of those, fortunately. All right, so the figures at the bottom. Vesta is one of those large asteroids. This telescopic photo of Vesta is not very good. We don't really see too much detail there because we've never sent a space mission anywhere near Vesta. So this particular photo, which I think is a Hubble photo, is not very good resolution. Eros over there, the asteroid of love, is actually one which has been passed by using a space mission. That's why we can see a very strange shape there, and the fact that it has its own craters. Okay, so the largest 4 asteroids that we know of in the solar system right now, as you can see, the diameters are hundreds to 1,000 kilometers. So again, these kind of continental, roughly sized bodies here. Semi-major axis of these largest 4 asteroids are right in that asteroid belt between Mars and Jupiter. Mars at 1.5, Jupiter at 4.5. These guys are all around 3 or so. So that's the asteroid belt that we talked about. The eccentricities are worth noting because some of them are pretty large. Like, for example, 25% eccentricity for Juno. Now, that's going to result in a pretty significant variation of distance from the Sun for these bodies, right? Because the larger the eccentricity, the farther away from a perfectly circular orbit you are, and the more wandering back and forth there is between from the Sun, distance from the Sun. The asteroid belt actually is a fairly wide zone, as we can see there, from about Mars' orbit out to about 3.5 astronomical units. And the reason we see a relatively large zone is because, again, this is not really a completely homogeneous group of bodies. They have different semi-major axes, they have different eccentricities. But notice we don't see too many beyond 3.5. Jupiter is at 4.5. That's the reason we don't see too many asteroids beyond 3.5, because they start getting too strongly affected by Jupiter's gravitational field, and Jupiter kind of clears out that zone. All right, so here's the asteroid belt on a plot to scale of the solar system. And we can see that the asteroid belt itself is really a feature of what we would think of as the inner solar system. And, we don't really talk about the outer solar system until we get to Jupiter and beyond. So this belt is between Jupiter and Mars. Jupiter and Mars, so this is sort of kind of the inner solar system. Now, when we start talking about comets, we're going to be talking about, again, two groups. One group out around Neptune and another group much farther away. All right, so asteroids mostly are in the asteroid belt, which I already mentioned, between 1.5 and 3.5 astronomical units. And the asteroid orbits have, a lot of them have relatively small eccentricities, some of them have larger eccentricities. But what that means is they basically orbit in this donut-shaped region here, and they happily live there, if this will work. But plug-in is vulnerable. We don't care about vulnerability. We're young, we're invincible, right? Even change. It's gonna work. Huh? Okay. Sorry. Okay, well, looks like this isn't going to work. I had shown this earlier in the semester, so I have no idea why hiding is not going to cooperate. Okay. But anyway, what we would see is basically kind of an animated version of this thing with those asteroids moving around the sun. All right, a little further into asteroids, we have the asteroid belt population, and we also have a few other populations of asteroids that have a special gravitational relationship with Jupiter. Now remember I said that we don't really get too many asteroids between 3.5 and 4.5 because there's a zone here that's basically swept out by Jupiter's gravity. It's sort of one of these examples of an orbital resonance. But there's another way in which Jupiter actually collects asteroids. The asteroids that tend to wander into this zone between 3.5 and 4.5, instead of just getting sort of obliterated, they actually get collected into two regions that are called Lagrange points that lead or follow Jupiter by 60 degrees of angle relative to the sun. And the reason that we get an accumulation of asteroids in these places is because it turns out those are stable places where the forces on them tend to be in balance. These are called the Trojan asteroids, the ones that are in these two groups I'm talking about. All right, so I just mentioned there are these things called Lagrange points. There's actually 5 of them. 1, 2, 3, 4, 5. Each of these Lagrange points, the significance of it is that if we add up all the forces acting on a body at a Lagrange point, the force is 0. Okay, so these are called equilibrium points because when we add up all the forces, it's equal to 0. Now, what forces am I talking about? Well, I just mentioned Jupiter, so there's going to be a force of Jupiter, that red dot over there. Jupiter is exerting a gravitational force on any of these points we're talking about. The sun is also exerting a gravitational force, and there's a third force, which is a centripetal force, because these objects are in orbit at these locations, and so there's a centripetal force, just like any spinning body has a centripetal force. Now what we're doing is we're balancing those 3 forces: force of gravity from Jupiter, force of gravity from the sun, and centripetal force. And if we do the math, it'll be expected to work out on the final exam. Sorry, I can do about that. What you get is 5 places. 5 places where you can get this equilibrium of forces. All right. Okay, so we'll talk about that in a moment, but there's another couple of classes of orbits I mentioned at the top of the view graph here. Okay, so we have the Lagrange, we have the Trojan asteroids that are at Lagrange points 4 and 5. We'll get back to that in a moment, but before I click off the slide, I want to mention that we also have these 2 other classes. Now the 2 groups at the top there have absolutely nothing to do with these Lagrange points. Those are 2 separate groups, but they're really of interest to us, especially the second one, the Apollo asteroids. Because the Apollo asteroids have a perihelion distance from the sun. Remember, perihelion is the closest approach distance to the sun. The Apollos have a perihelion distance that's less than 1 astronomical unit. Now here we sit at 1 astronomical unit from the sun. So if those Apollo asteroids have a perihelion distance that's less than 1 astronomical unit, they could cross Earth's orbit, right? So the Apollo asteroids are the ones which could potentially threaten to strike Earth. So we're really interested in knowing about them. We know about thousands of them already of various sizes. And if, the Apollo asteroids are the ones that could potentially strike Earth. The Armor asteroids play a similar role with Mars. They're the ones that cross Mars's orbit. Okay, now keep in mind that just because the orbit of an Armor asteroid crosses the orbit of Mars's asteroid, that doesn't mean they're going to collide necessarily, because they both have to be at the same place at the same time, right? Just because here's Mars's orbit, and here's an Armor asteroid, it could cross the orbit of Mars, but maybe Mars isn't there when it crosses. So you're not necessarily going to get a collision. Just like with the Apollo asteroids, they're not necessarily going to hit the Earth. They have to still be in the same place at the same time, right? And for example, the asteroid that caused the extinction of the dinosaurs hundreds of millions of years ago was an Apollo asteroid. We